Alright, this is Computer Science 305, Programming Languages, and today we're going to be talking about ML for the second time. So, this is our second look at ML. Today we're going to be talking about patterns in ML, as well as local variable definitions, and then we'll walk through a quick sorting example. So there's two patterns we already know, right? We've seen ML functions can take on a single parameter. For example, the function f that takes n and returns n times n. And we've also seen how we can specify functions more than one input by using tuples. Similar to the function f that takes in ab and returns the value a multiplied by b. Both the individual n and the tuple ab are patterns. The n matches and binds to any argument, while ab matches any two tuple and binds a and b to its components. There's also the underscore as a pattern, and this one will actually operate. So say font f underscore equals, and then yes, right? And so it matches anything, and then it returns a string, as we expected, right? So if we say f 34.5, we get yes back, right? The whole point of this is the underscore is used when we don't want we don't really care about what is being matched. Just that we can anything coming in is fine. It's preferred to using f of x because when we use f of x, it basically is binding a variable, whereas the underscore binds to nothing. So bear that in mind. Constants as patterns. We can also use a constant as a pattern, right? So if we were to define fun f0 equals yes, as we just did, it does give us this warning, match non-exhaustive, as you can see in the slide. And that basically is telling us that we're not matching all possibilities for it taking in an integer of sorts. So, because as we can see that the actual value of the function f, the type is an integer that returns a string, or maps to a string, but we only are capturing one of the possible integers that could be there. So what we would like to do is be able to use this later when we're dealing with things, right? So any constant of equality type can be used as a pattern, but not, for example, a constant like a real, right, which cannot be matched as an equality type. So we cannot say fun f 0.0 equals yes. It will give us an error, right, because real does not have an equality operator. So non-exhaustive match, right? In that last example, the type f was mapped to string, but with a match non-exhaustive warning, right? Meaning that f was defined using a pattern that didn't cover all the domain, right? As I just said. So you may get runtime errors like this. F of 0 val it equals yes, which returns a string, and then you get f of. Then if we call f of 1, right, it gives you this uncaught exception non-exhaustive match failure. So we need to be aware of this. List of patterns is patterns, right? So we can define a list, right, as our input to a given function. So you can use a list of patterns as a pattern. So this example matches any list of length 2, treats a and the underscore as subpatterns, binding a to the first element of the list. So for example, we can redefine f to be a underscore, right, as our list, and it just returns a. So it gives us the same non-exhaustive match issue, but what we can do is we can say f, and we can give it the character f and the character g, right, and it returns f, right, the first character. So it works. So we can also do cons of patterns as a parameter, and this one's actually really interesting, especially for like the upcoming lab that you have in ML. Oftentimes, if we give them a cons list, right, or a cons as our input parameter, it gives us the ability to manipulate both the head and the tail of the list, right? So the head of the list and then the remainder of the list. So if we say f function f x xs, right, Well, it gives us this non-exhaustive match, right? It tells us that we can take in a list of any type and return essentially the value that is contained in the list, the first item, right? Or sorry, it returns the head of the list. Well, that's all good. The problem here is this does not handle null list, and so we need to deal with that, right? So basically, what we're saying here is that x cons xs matches any non-empty list and binds x to the head and xs to the tail, right? Note that I said non-empty list, right? So non-empty list means that it will not capture the nil list or the empty list. So that's why it's giving us that match non-exhaustive warning. So we can, and then we use the parentheses around the list definition, the cons definition, for precedence. We have to have that. Otherwise, it will try to match on x and then cons that to xs, which is weird. But so if we were to operate this, we say on the 1, 2, 3, we expect it to give us the 1 in return, of course. It applies to any type of list. We could have characters as well. And we can also do a list with just one item in it. So it works, right? If we try to use the empty list, though, it will give us an error, right? Value restricted, so we can't do that. Okay. So what we have seen so far, right? We've seen a variable is a pattern that matches anything and binds to it. An underscore is a pattern that matches anything, just in general with no binding. A constant of any quality type is a pattern that matches only that constant. A tuple of patterns is a pattern that matches any tuple of the right size, whose content matches subpatterns. A list of patterns is a pattern that matches any list of the right size, whose contents matches subpatterns. And a cons of patterns is a pattern that matches any non-empty list whose head and tail match the subpatterns. These are all really great patterns that can help us do a significant amount of the work that we need to do in ML. So we can also have multiple patterns for functions, right? So this is where these really interesting recursive definitions start to come in. So we can just like we could in BNF, we can have alternations when we're defining patterns for functions. So we can either define the function multiple times, or we can just define it once and then use an alternation to define other possible choices, right? So for example, in the one that we show here, we have the function f0 and it returns the string 0. And then we can have f1 return the value 1. And so these are two possibilities, right? So then if we say f of 1, it returns 1. If we say f of 0, obviously it returns 0. But if we say f of 2, it returns that it has a match failure. So let's see. Okay. Anyhow, the syntax is basically that we have some function we use the function definition, right? This is syntax for function definition in ML, right? So we have to have the keyword fun, and then a function body followed by a semicolon. Function bodies can be defined either by a typical function body or by a function body followed by a vertical bar followed by function bodies, where a function body is defined by a function name space, a function name followed by a pattern followed by the equal sign and then an expression. To list alternate patterns for a function, you must repeat the function name in each alternative, right? So, as fun as that was, so now we can have overlapping patterns, right? So patterns may overlap, right? And then ML is going to use the first match for a given argument. So, if we were to redefine this, say we have a function f0 equals 0, right? And then we have the alternate f and then underscore, which matches anything, equals non-zero, right? If we were to do this, f of 0, right, will match the first one it finds, the first pattern defined, which is the 0 pattern, and we'll return 0, right? And then we type in anything else to, it will match non-zero. 99 matches non-zero. Alright, and even if we say f of -1 matches non-zero. Alright, so ML uses the first match for a given argument. The pattern matching style, right, so what we just did, where we had the f of 0, f of underscore, for 0 non-zero, we can also define using an if then else statement, which would be, example would be fun f n equals, then we'll, if n is equal to 0, then 0, else non-zero, right? So then we say f of -1 gives us non-zero, f of 0, 0. So the pattern matching style usually is preferred, where we use the alternatives. One is cleaner looking, more legible, but it also is closer to what we'll call recursive definitions that we'll see later in the examples. So, for example, if we recall from the previous ML lecture, that we defined the factorial function, fact n equals if n equals 0, then 1, else n times fact n minus 1, right? Which was great, but a cleaner, more elegant looking version is the one that we show here, which is the recursive definition, right? The what we'll say a much more cleaner recursive definition, where we're moving the key here in understanding what we're doing is we're going to break this down into two different alternates, which are also n equals 0 is our base case, right? And then the else is our recursive case. So we can actually define that as we define one pattern being our base case, or base cases as we need to define, and then we have the general case, which is our recursive case, and it just looks so much cleaner. I'm going to see if I can't make this a little easier for everyone to see. Alright, so we can redefine this as fun fact 0 equals 1, and then we'll create the alternative. This fact n equals n times fact n minus 1. It just looks so much cleaner when we define it in this way. And we can also say fact 99, which gives me an overflow error. So let's try fact 15. And can we actually get one that gives me a value? That would be great. There we go. Without causing overflows. Alright, so we can also define the reverse function, right, which simply reverses a list. If we look at this one, the previous version, which is the if-else that we saw before, we can actually define it in a much cleaner way. If we say function reverse nil, right, which takes in nil, and this is getting into where now we're using the pattern for the cons pattern, right, which looks so much slicker. So we say first rest equals, and then we'll just do it all in one line. Right? So we're going to concatenate and reverse. So and then we run this, right? So if we have a function, so we have to have a list, say reverse 1, 2, 3. It returns 3, 2, 1, right? Looks good. So there's lots more examples, right? This structure occurs frequently in recursive functions, as I've been saying, that operates on lists. One alternative for the base case, nil, and one alternative for the recursive case, first, the head and the rest of the tail of the list, right? So we adding up all the elements of the list, pretty simple, right? Basically a summation. So we say fun f nil equals 0, right? Because we assume that if it has nothing in it, then its value is 0. And we say f first rest equals first plus f rest, right? We say do the same thing. Call f on 1, 2, 3 should return 6. It returns 6. Excellent. Counting true values in a list, pretty easy day, right? So if we say function f nil equals 0. Give the alternate f true rest equals 1 plus f rest, right? And then we say f when we have a false as the head, right? So that's what our two cases. The head is true or the head is false. Then we can call just f rest, right? So this is our nil is the base case, and then we have two alternatives for our general case, right? Whether or not the head is true or false. So this allows us to define it in such a way that we have this nice compact view of the function using the cons pattern. And so now if we call f on true, true, false, right? We should see 3. Right? Because that's the number of trues that we had. Does that make sense? So then we, if we want to make a new list of integers, right, in which each one is greater than in the original list. So what we can do is we say fun f nil equals nil, right? And then we create the alternative. So obviously, if the list is already empty and nil, there's nothing for us to do. So we just return the nil list. Otherwise, we take in a cons pattern for a list so we can operate. And then what we're going to do is we'll update the first one, first plus 1, right? Cons with f on the rest. So this is going to walk recursively, starting at the very head of the original list, and add 1 to that for each one that as it goes down. So we should, if we were to run this, say on f on 1, 2, 3, we should see a return of a list of 2, 3, 4, which is what we get. So there is a restriction, right? You can't use the same variable more than once in the same pattern. So for example, function f of AA, the pair AA, right, for pairs of equal elements, or the function FAB, right, we can't do this because we're using AA in the first one. It doesn't make any sense. Instead, we have to use an actual breakdown where we have AB and then we have to check for equality. So, for example, if we were to actually attempt this, let's just to see what we'd actually see. We say fun f AA equals, and we'll just say A, and then our alternative would be f AB, and we just return B. What this will return is a duplicate variable in patterns A, right? So that's going to cause us a problem. That's why we would end up having to say create the function f where it takes in AB, and then we would have to say if A equals B, then A else B, right? And that will give us the right answer. So on the other hand, we can have a poly-equal warning, right? It's a warning for equality comparison when the runtime type cannot be resolved. So this is the problem, right? Because we have to ensure that the type of incoming value needs to be at least an equality comparable value, right? So not real, but could be a string or a character or you know, a variety of different other types, right, that are actually equal comparable, right? So if we create a function fun eq ab, and we say if a equals b, then 1, else 0, right? So warning, calling poly equal, right? That's not good. So this will work if we say eq1 3, right? And then if we say eq abc returns 1. So you know, it's a warning for equality comparison when the runtime type can't be resolved. It's okay to ignore this kind of equality test as inefficient, but can't always be avoided, right? It's going to and so we just need to be aware that it's a weaker form of well, it's not a weaker form of equality test. It's an inefficient form of equality test because it's not specific to any type, and it has to actually do work to resolve the type first, then to actually produce an equality operation. It would be faster if we were using a specific type of a typed equality operator, but that's not always the case. Patterns everywhere, right? So there are lots of different patterns available, and we'll see them all over the place, right? And typically whenever we're doing what we're doing, patterns are not just for function definition, right? Here we in this example that we see here, right, we have patterns that are representing in the val, right? So a variable that we've created, we can actually create a pattern base for that. And then there will be lots of other places where we actually can use patterns throughout ML. For example, when we create types and stuff like that. So the val type was the values to patterns was as shown, right? So it gives us two different bindings for the values that we've assigned it to. We could also use the cons pattern as we saw earlier, which is 1, 2, 3, 4, 5, which that will bind a right. Oh, sorry. Yeah. So that will bind A to the head and B to the tail of the list. So it's not too bad. It's pretty easy to understand these patterns. They are fairly intuitive if you sit down and think about it based on what we know about ML so far. So moving forward, I'm going to stop here and then we'll restart at the local variable definitions.